It is part 2 of section 8.2. Here we'll study the symmetric power method and the inverse power method, which are variants of the basic power method. The symmetric method is for eigenvalues of symmetric matrices, while the inverse method is for eigenvalues near a prescribed number. Let's see details, beginning with the symmetric method. We have a theorem called the spectral theorem. Suppose a square metric is symmetric. Then we have these properties. A has n eigenvectors, v1 to vn, such that the set of eigenvectors is on orthonormal basis for Rn, which means that, first of all, these eigenvectors are linear independent, and we can orthogonalize and normalize to get on orthonormal basis for Rn. Every eigenvalue of A is a real number. Eigenvectors corresponding to distinct eigenvalues are orthogonal. That means that we have two different eigenvalues which are different, then corresponding eigenvector, for example, v1, and now corresponding eigenvector v2, then here v1 dot v2 is 0. Okay. There exists a diagonal matrix D and an orthogonal matrix U such that it can be written this way, which means that A is diagonalizable. A is U D U transpose. Is orthogonal matrix has property, and U transpose U is identity. That means that U transpose is U inverse. Okay. Diagonal entries of D are eigenvalues of A, and the columns of U are the corresponding eigenvectors. Now, this one implies this one quite simply. Okay, let's say the corresponding eigenvalues are lambda j, then that means that here A Vj equal lambda j Vj. Okay. Now we rewrite this one, then we multiply U to the right side, then U transpose U will be identity, so that AU is the same as UD. Okay, this one, and it's a metric. If we consider the columns, then each column will be from left hand side, jth column will be AVJ, right side will be lambda j Vj. So that this implies that quite easily. And once the given matrix is symmetric, the power method can be formulated along with L2 norm rather than L infinite norm to get faster convergence. Here we have a pseudocode for the symmetric power method. A is symmetric. Then start with non-zero vector, and we initialize x0 to become length 1 in L2 norm, so that divided by x2 norm. Now, almost same as the original power method. Here, multiply first. Now, A, and now save here, and we measure the magnitude in L2 norm and scale to get new iterates. Now, mu k is updated in this way. Mu k is dot product along with here this one, and then now here xk minus 1, all the iterates. In this way, we try to update. Then, and theoretically, we can prove that mu k is converging to lambda 1 rather than lambda 1 absolute value. The lambda 1, and here there is now, and the error term is earlier we have each time here reduction is lambda 1 over lambda, okay, lambda 2 over lambda 1, but now it's squared. That means that symmetric method converges twice faster than the basic tower method. Okay, so but update manner is this one. Okay, you may roughly consider this one. Now, once k is large, then eventually yk and early iterate has almost the same direction, so that this dot product will be now yk norm times xk minus 1. Now norm is L2 norm, of course, and then cosine theta. This is the well-known formula. Once they are almost the same direction, then there will be almost 1. Now here this is 1, so that this quantity is now almost same as that one, so that here that is really the scaling factor. Okay. Okay. Let's consider the same metric we considered earlier for the basic symmetric, basic power method. Now we know that 3 eigenvalues are 6 and 3 and 1. Okay, this is maple implementation of the symmetric power method. And first, multiply A and save into Y, and that is a mu k update evaluation, and we measure L2 norm and scale. And similarly, we try to print out, and now error is measured from the largest eigenvalue. Okay. Here, after 10 iteration, now is way better than basic power method. And in L2 norm, since we have the eigenvector 1, minus 1, and 1, but it's scaled so that it's length 1. Now, we know that we can easily see the error becomes quarter, again quarter. Now, lambda 2 over lambda 1 is half, and 6 and 3, so half, but a half squared is quarter. So that in each iteration, the error is reduced by factor 4, so it's twice faster. Okay. Now we have accuracy analysis. Okay, we are in this algorithm And here, so y, that is x multiplication, and through this one we try to get now mu k, so that when we apply stopping criteria, then the stopping criterion is based on eventually ax minus mu k. So once it is small, then we can stop the iteration. But here we have a theorem. A is symmetric, having eigenvalues of lambda 1 to lambda n. Then for any vector having length 1 in L2 norm and mu n is scalar, now ax minus mu x in L2 norm is upper bound of that minimum value. For any mu, this quantity is always larger than or equal to this quantity. You can find some eigenvalue such that, so it's a minimum, the measuring from mu to lambda I, among all eigenvalues, you can find the minimum value. This minimum is always less than or equal to this norm, which means that this can be used for stopping criteria. And then once it is smaller than, for example, 10 to the minus 10, then practically the computed mu k will be near to the desired eigenvalue with the same order. So the 10 to the minus 10. Okay. Here we have a proof. If you are interested in the theory, then you may try to read the proof. Okay, let's go to the inverse power method. Some applications require to find an eigenvalue near a prescribed value Q. The inverse power method is a variant of the basic power method to solve such a problem. Here we have derivation. The inverse power method will use such a metric. Once Q is given, then we try to understand what eigenvalues and eigenvectors of this metric. Okay, in this derivation, start with metric A. Okay, it has eigenvectors vi and corresponding eigenvalue lambda I. Okay, start with this one. Once qi is subtracted, then in right side for eigenvalue minus q. Okay, from here, there you can get quite easily. Now we multiply a minus qi, the inverse, and both sides, so that it will disappear. Inverse will appear here, and divide by lambda I minus q, so that we put this one over there and here. Then we reach that one. This is a simple algebraic manipulation. But this means that now for this metric, and eigenvectors are same as those of A. Now the corresponding eigenvalues are 1 over lambda I minus q. So here eigenvalues can be written in this way. In our inverse power iteration, we'll try to multiply this metric again in each iteration, and the corresponding eigen vectors will be eigenvalues will be like that, so that among these values we'll get the largest one. Once the largest one is obtained, then out of the largest one, we can recover the corresponding eigenvalue for A. Now, in iteration, we'll get mu k, but mu k is representing an approximation of 1 over lambda minus q, and so that'll be the largest quantity among that one. And so that the corresponding eigenvalue lambda can be obtained this equation, from this equation, solving for lambda. So reciprocal and add q, then we reach that one. Let's see a pseudocode for the inverse power method. We apply the basic power method to that metric. That is the inverse power method. To start with x non-zero, and here, okay, that is, okay, I missed here, and in fact, that must be x infinite norm. This is typo. Must be initialized in this way. I'll correct the lecture note. Okay. And here, we multiply now the metric and get u1, yk temporary vector, and measure the length and divide by the length in infinite norm, so we can get new iterate. Now, for mu k, we can get lambda, the corresponding lambda, and like using this equation, so that 1 over mu k plus q is lambda. So lambda will approach to the desired, the eigenvalue nearest to the given number q. Okay. Let's see here. The same metric again for that one. And we already know that here the eigen values are 6, 3, and 1. So the q is chosen 5 over 2. So here, and the eigenvalues of a minus qi inverse, the eigenvalues can be, okay, let's go back over there, lambda 1 minus q, 1 over lambda 1 minus q, and so on. So that is 1 over lambda 1 is 6 minus, okay, that is 2.5. And second eigenvalue of this metric will be 1 over 3 minus 2.5. And last eigenvalue of this metric will be 1 over 1 minus 2.5. Okay, this quantity is 1 over 3.5. Okay, now that one is 1 over 0.5, and this one is 1 over minus 1.5. Right? So that is the largest eigenvalue. Practically there's 2, and practically this one is now, okay, this is 2 over 7. Okay, this one is minus 2 over 3, right? Largest eigenvalue. Okay. Now, start with here vector, non-zero vector, q is 5 over 2, and now we are now applying an IDS identity mapping. So each time inverse is multiplied. But in the beginning, you can find inverse, and you can just simply multiply in each iteration. But here, to get the same form, I wrote it down in this way. So each time inverse is found and then multiplied. Now measure L infinite norm, the length, and scale. Now by using the formula, we try to get in mu k. That is now the eigenvalue of original metric A. So it's near around 3, so that we measure the error from 3. Okay, let's see here. Now, okay, after 10 iteration, look at the convergence, and then now error becomes order of 10 to the minus 9. Now 2.5 is near 3, and the ratio between this one, that one, and is 7, and this one, that one is 3. But here, in fact, now for the original one, and from the analysis, we can see that this one is the combination of, in fact, in V1 and V2, so that there is no V3 component. So here, in each time, the error is reduced by a factor of 7. So it's almost 1 digit, but not really 1 digit. So it is 7 times smaller, 7 times smaller, 7 times smaller. The reason is, anyway, now the second largest one is this one, but ratio 3, but there's no component from over there. So that this is dominant. Okay, this is what we want to get, and this one is the ratio between these two will make the convergence speed. So it is 7 times smaller. Okay. Okay. Now the inverse power method also can be implemented for the symmetric method, because the metric is a symmetric, and also we apply the inverse power method for symmetric matrices. So because we start with this symmetric metric. Okay. Okay. Now symmetric version of the inverse method, and along with Q the same 5/2, and we measure the error from 3. Look at here after 10 iteration. Now the error is order of 10 to the minus 16. Again, symmetric power method converges twice faster than basic power method. It's inverse version or original version, it doesn't matter. The symmetric method is twice faster than basic method. Okay. Okay, that's the end of chapter. Section. Thank you.